There is a place in the universe where the laws of physics break down completely. Not bend, not stretch, not strain at their edges until they grow uncomfortable and creak with tension. They break, completely, irrevocably, and without apology, as if they never existed at all, as if everything we have spent 4 centuries learning about how the universe works simply stops applying. Imagine standing at a cliff's edge. You know where the ground ends. You can see the boundary. Beyond it, things fall. That is physics operating normally. Gravity, momentum, trajectories, all following rules we can write down and test and verify. Now imagine a cliff where the rules themselves fall. Not you, the rules. A place where time, the one dimension we have never managed to step outside of, the river that has flowed in one direction since the first moment of creation, slows. Not in the way it slows when you are bored or frightened, not as a matter of perception, slows physically, measurably, verifiably. An observer watching from a safe distance would see a clock near this place tick slower and slower and slower, its hands approaching, but never quite reaching a final moment, the last tick stretched across eternity. And closer still, past that stretched moment, time stops entirely. Not metaphorically, not approximately, it stops. And light, the fastest thing the universe permits to exist, the messenger that carries every piece of information we have ever gathered about everything beyond arm's reach, the thing that allows us to see, to observe, to know, light enters this place and does not come back. It spirals inward, it curves, it crosses a threshold, and from our side of that threshold, it simply ceases to exist as something we can ever know about. We call these places black holes, and for most of the history of the science that predicted them, we treated them as extreme but ultimately marginal features of the cosmos, mathematical inevitabilities, curiosities born from equations pushed past comfortable limits, things that existed in the sense that prime numbers exist, real within their formal system, but somehow not quite part of the world you walked around in every day. We were almost certain they couldn't really matter, not in the grand scheme of things. We were wrong. In the last 2 decades, a cascade of discoveries, each more staggering than the last, each arriving before the community had fully processed the one before, has overturned nearly every comfortable assumption we had built up about these objects. We have heard 2 of them collide. Not seen, heard in the sense that we detected the gravitational wave equivalent of sound, a chirp of compressed and expanded space-time that had been traveling toward us for 1.3 billion years, generated by a collision that released more energy in a fraction of a second than our sun will radiate across its entire 10 billion year lifetime. We felt that chirp as a displacement of our most sensitive instruments by an amount smaller than 1/10,000th the diameter of a proton. We have photographed one, actually formed an image of its shadow of the event horizon, the boundary of no return, silhouetted against the orange glow of superheated gas spiraling around it. The image required coordinating 8 radio telescope arrays on 5 continents, creating a virtual instrument the size of planet Earth, collecting 4 petabytes of data, and then spending 2 years developing new computational methods to turn that data into a picture. We did all of that, and the picture we got matched with stunning precision the predictions of equations written down in a World War I trench in 1916. We have found them lurking at the center of virtually every large galaxy in the observable universe. Not some galaxies, not most galaxies, every large galaxy we have looked at carefully enough, including ours. Including the Milky Way, the galaxy you are sitting inside of right now, whose center lies in the direction of the constellation Sagittarius, 26,000 light-years away, occupied by a sleeping monster 4 million times the mass of our Sun, a monster that has been sitting there before the solar system formed, before complex life emerged on Earth, before the first fish pulled itself onto land. But here is where things become truly, deeply strange. Here is where the story stops being merely spectacular and becomes something more unsettling. The more we learn about black holes, the more carefully we look, the more precisely we measure, the further we push the mathematics, the more they appear to be not just objects that exist within the universe, but something far more fundamental, far more essential, far more deeply entangled with the universe's history and structure than anyone anticipated. The galaxies that exist, the particular distribution of their sizes and masses, the stars that form within them, at what rate over what time scale, the thermal state of gas across millions of light-years of space, the chemical evolution of the interstellar medium that eventually produced the raw materials for planets and life, the conditions on our own world that made complex chemistry possible. All of it, we are learning, bears the fingerprints of black holes. What if they are not the destroyers we imagined? What if the darkness at the center of every galaxy is not a wound in the universe, but the hand that shaped it? What if, in the deepest, most philosophically vertiginous sense of the word, black holes are the reason anything like us is here to be asking these questions? Today, we journey through the evidence, all of it. The historical discoveries and the observations from orbit and the gravitational wave detections and the computer simulations that fail without black holes and succeed with them. We will follow the mathematics to places it has never quite taken us before, and we will sit with the questions it raises that remain unanswered. Prepare yourselves. We begin.
Every great discovery has a prehistory, a period before the discovery when the idea existed only in fragments, when someone almost got there, when the conceptual tools existed, but the will or the timing or the audience wasn't right. The prehistory of black holes is longer and stranger than most. It begins not in the 20th century, not with Einstein and his revolution in our understanding of space and time, but in the 18th century, in a country rectory in England, with a man whose name almost no one knows. John Mitchell was born in 1724. He studied at Cambridge, became a Fellow of Queen's College, taught geology and mathematics, made important contributions to the understanding of earthquakes. He is sometimes called the father of seismology, and eventually became a country rector in Thornhill, Yorkshire. He was, by all accounts, a man of wide learning and considerable original thought, the kind of figure the 18th century produced in some abundance, someone whose intellectual range encompassed multiple disciplines before the age of specialization had narrowed what a single mind was expected to master. In 1783, Mitchell wrote a paper. It was addressed to Henry Cavendish, the eccentric and brilliant British chemist and physicist who would later measure the gravitational constant. The paper's subject was the nature of light from distant stars and how it might be affected by gravity. Newton's theory of gravity was less than a century old at this point. It was already the greatest theoretical achievement in the history of science, a mathematical framework that described the motion of planets, the trajectory of comets, the falling of apples, the rise and fall of tides, all as consequences of a single universal force that decreased with the square of the distance between objects. It was breathtaking in its scope and precision. Newton himself had imagined light as consisting of particles, tiny corpuscles, fired outward by luminous bodies. If light was made of particles and gravity acted on particles, then gravity could in principle act on light. It would be a very small effect. Light moved so fast that gravity would barely have time to act on it before it was gone, but the effect would be there. Mitchell followed this reasoning to its conclusion. He asked, what if a star were so massive and so compact that the escape velocity from its surface equaled or exceeded the speed of light? Escape velocity is the speed at which you need to launch an object upward in order for it to escape a gravitational field entirely, rather than falling back. For Earth, escape velocity is about 11.2 kilometers per second. For the Sun, it is about 617 kilometers per second. Both of these are far below the speed of light. But for a sufficiently massive, sufficiently compact star, a star compressed into a small enough volume, the escape velocity could reach the speed of light. And if it did, then even light corpuscles, fired outward from the star's surface, would be pulled back by gravity before they could escape. The star would be invisible. It would give off no light detectable from a distance. You could only know it was there by its gravitational effect on nearby objects. Mitchell called these objects dark stars. He estimated the size a star of the Sun's density would need to be in order for this to happen. He came up with a radius of about 500 times the Sun's current radius, enormous, but not unimaginably so. He sent the paper to Cavendish and to the Royal Society, where it was published in the Philosophical Transactions. It was read, it was acknowledged, and then the scientific community moved on because there was no observational evidence for such objects, no pressing theoretical need for them, and the conceptual framework of the time, Newtonian mechanics, a static and eternal universe, stars as fundamentally similar to the Sun, provided no strong motivation to take the idea seriously. Pierre-Simon Laplace, the great French mathematician and physicist, reached the same conclusion independently, publishing it in his book on celestial mechanics. He included it in the first two editions, then quietly dropped it from subsequent ones. Perhaps the idea seemed too speculative. Perhaps he worried it made him look credulous. The gravitational dark star disappeared from French scientific discourse. For 120 years, Mitchell's dark stars slept. Then, in the autumn of 1915, a 36-year-old patent clerk turned professor, turned the most celebrated physicist in Europe, sat down and completed what many consider the greatest intellectual achievement in the history of science. Einstein had spent 10 years trying to reconcile his 1905 special theory of relativity, which described how space and time behave for objects moving at constant velocities relative to each other, with the existence of gravity. Special relativity said nothing about gravity. It lived in a flat, unaccelerated universe, and yet the universe clearly contained gravity, clearly contained acceleration, clearly contained massive objects, warping the behavior of things around them in ways that special relativity couldn't describe. The resolution Einstein found was so radical that even he was sometimes astonished by its implications. Gravity, he concluded, is not a force at all. It is geometry. Space and time are not separate things. They are woven together into a single, four-dimensional fabric called space-time, and matter and energy warp this fabric. A massive object sitting in space-time creates a curvature around it, the way a heavy ball creates a depression in a stretched rubber sheet. Objects moving through this curved space-time follow the straightest possible paths, called geodesics, and those paths, in the presence of curvature, are not straight in the ordinary sense. They curve, they bend, they spiral inward, and we experience this bending of geodesics as what we call gravity. In November 1915, Einstein presented his completed field equations to the Prussian Academy of Sciences. They related the curvature of space-time, described by a mathematical object called the Einstein tensor, to the distribution of mass and energy, described by the stress-energy tensor. 10 coupled, non-linear partial differential equations, the most complex and beautiful equations in physics. Einstein himself believed the equations were too complex to be solved exactly, except in trivial cases. He expected physicists would work with approximate solutions for generations. He underestimated Carl Schwarzschild.
Carl Schwarzschild was 51 years old in 1915, and he had volunteered for the German army despite his age. He was serving on the Russian front, calculating artillery trajectories. He was also, apparently, reading physics papers in whatever spare time the war allowed him. In December 1915, Schwarzschild obtained a copy of Einstein's November papers and within weeks had solved the field equations exactly, finding the precise mathematical description of spacetime around a perfectly spherical, non-rotating, electrically neutral mass, a solution that Einstein had not expected anyone to find. The Schwarzschild solution, as we now call it, is elegant. It describes the geometry of spacetime in the vacuum surrounding a spherical mass, a star, a planet, anything that is round and not rotating. It tells you how clocks run, how rulers measure, how light bends as a function of distance from the center of the mass. And it contains something that disturbed Schwarzschild deeply. At a particular radius, now called the Schwarzschild radius, the mathematics behaved strangely. Terms in the equations that were supposed to describe distances became infinite. Terms describing time went to zero. The mathematics appeared to break down at this surface in a way that suggested something extraordinary was happening there. For a mass equal to the Sun, this critical radius was about 2.95 kilometers. For Earth, it was about 9 millimeters. For a person of average mass, it was about 10 to the minus 25 meters, far smaller than a proton. These numbers told a story. To create a black hole from the Sun, you would need to compress all of its mass, all 2 times 10 to the 30 kilograms, 2,000 billion kilograms, into a sphere less than 3 kilometers across. To create a black hole from Earth, you would need to crush our entire planet into something smaller than a marble. Schwarzschild mailed his solution to Einstein in January 1916. Einstein was visibly impressed. He wrote back praising the work, noting that he had not expected the problem to be solved in such clean form. 2 months later, Schwarzschild was dead. The skin disease he had contracted in the trenches, pemphigus, had progressed too far. He was 52. He never knew what his solution would eventually mean for physics. He probably had some idea that the critical radius was important, but the full physical interpretation, the event horizon, the singularity, the nature of what lay within, took decades more to develop. For the next 4 decades, most physicists interpreted the Schwarzschild radius as a coordinate artifact, the kind of apparent weirdness that arises when you use the wrong coordinate system to describe a smooth manifold. Like how the surface of Earth appears to have a singularity at the north and south poles if you use latitude-longitude coordinates. The poles are not actually singular. They are perfectly ordinary points on a smooth sphere. The singularity is in the map, not the territory. Maybe, physicists reasoned, the singularity at the Schwarzschild radius was the same kind of thing, a map problem, not a territory problem. Maybe if you transformed to better coordinates, the weirdness would go away. In 1958, the American physicist David Finkelstein published a paper showing that the Schwarzschild radius was indeed a coordinate artifact in one sense. You could transform to coordinates in which the metric remained well-behaved there, but that this did not eliminate the physical significance of the surface. In the new coordinates, the Schwarzschild surface was revealed to be a one-way membrane. Matter and light could pass inward through it, but never outward. This was the first clear mathematical articulation of what we now call the event horizon. And it meant that the interior of a Schwarzschild black hole was not just a theoretical construct,
It was, in principle, a real place, a region of space-time that existed but that was causally disconnected from the exterior universe, a place from which no future directed path through space-time led back out. The universe was not going to be as simple as physicists had hoped.
While the theorists were wrestling with Schwarzschild's mathematics, observers were grappling with a more immediate question. We knew that stars died. We could see the remnants of dead stars, white dwarfs, small and dense and slowly cooling. The question was, what was the final fate of a star? Was a white dwarf the end point of all stellar evolution, or was there something beyond? Subramanian Chandrasekhar was born in Lahore in 1910 into a Tamil Brahmin family with a strong tradition of scholarship. His uncle was C.V. Raman, who would win the Nobel Prize in Physics in 1930 for the discovery of the Raman effect. Chandrasekhar was brilliant, driven, and mathematically gifted in a way that was apparent from early in his education. In July 1930, at the age of 19, he boarded a steamship in Madras bound for England, where he had won a scholarship to study at Cambridge. The journey took 3 weeks. He spent much of that time at a desk in his cabin, doing physics. He was thinking about white dwarfs and their quantum mechanical structure. White dwarfs are supported against gravity not by nuclear fusion, the fuel is exhausted, but by electron degeneracy pressure. This is a quantum mechanical effect arising from the Pauli exclusion principle, the rule that says no two electrons can occupy the same quantum state simultaneously. When you try to squeeze electrons together, this principle resists, not through any classical force, but through the mathematics of quantum mechanics itself. The resistance is real and powerful enough to hold up a star. The standard treatment of this pressure, developed by Ralph Fowler, treated the electrons non-relativistically, as if they were moving much slower than the speed of light. This was a reasonable approximation for most purposes, but Chandrasekhar noticed that it was not exact, and he was curious about what happened when you included special relativity properly. As a white dwarf becomes more massive, gravity increases, and the electrons must be confined to smaller and smaller volumes. By the uncertainty principle, smaller confinement means larger momentum. Larger momentum means faster motion. As the electrons approach relativistic speeds, fractions of the speed of light, their behavior changes in ways Fowler's treatment didn't account for. When Chandrasekhar did the calculation with full relativistic corrections, he found that the degeneracy pressure was weaker than the non-relativistic approximation suggested. And this weakness grew with mass. At a critical mass, approximately 1.4 times the mass of the Sun, the relativistic degeneracy pressure could no longer support the star against its own gravity. Above this mass, a white dwarf was unstable. It would collapse. Chandrasekhar worked on this result over the next 4 years, refining it, checking it, extending it. He wrote papers on it. He presented preliminary results at conferences. And in January 1935, he presented his complete analysis to the Royal Astronomical Society in London. The presentation was a disaster. Not scientifically, mathematically his work was impeccable, but socially, professionally, personally. Arthur Eddington stood up immediately after Chandrasekhar finished speaking. Eddington was the most famous astrophysicist in the world at the time, the man who had led the 1919 expedition to observe the solar eclipse and confirm Einstein's prediction that gravity bent starlight, the man whose announcement of that result had made Einstein an international celebrity overnight. Eddington was a giant of British science, a figure of enormous authority and prestige. He told the assembled fellows of the Royal Astronomical Society that Chandrasekhar's conclusion was an absurdity.
He had no physical argument against the mathematics. He had no alternative calculation. He offered no mechanism by which nature would prevent the collapse. He simply insisted, with the full weight of his authority and his contempt, that the conclusion could not be right. No star, he declared, would behave in so ridiculous a way. Nature must find a way to prevent unlimited collapse. Chandrasekhar was 24 years old. He had been in England for 4 years. He was still establishing himself, and the most powerful voice in British astrophysics had just publicly declared his most important work to be nonsense. He tried for some time to engage with Eddington's objections. He found that Eddington had no physical objection, only a metaphysical one. The result was too extreme to accept, and so it must be wrong. This is not how physics is supposed to work. Chandrasekhar eventually gave up trying to convince Eddington and largely stepped away from this line of research. He moved to the United States, took a position at the University of Chicago, and spent the following decades making foundational contributions to other areas of astrophysics: stellar dynamics, radiative transfer, hydrodynamic stability, the theory of black holes later in his career. His work was meticulous, rigorous, and beautiful. But the wound from 1935 never fully healed. In October 1983, the Royal Swedish Academy of Sciences announced that the Nobel Prize in Physics would be shared between William Fowler and Subrahmanyan Chandrasekhar, the latter for his theoretical studies of the physical processes of importance to the structure and evolution of the stars, explicitly including the mass limit that bears his name. Chandrasekhar was 72 years old. He received the call at his home in Chicago. He later wrote that he felt more than joy, a profound sense of vindication that had been a long time coming. Eddington had been dead for 37 years. The Chandrasekhar limit is now one of the most important numbers in astrophysics. It governs not just the fate of individual stars, but the entire chemical evolution of the universe, because the type 1a supernovae that occur when white dwarfs accrete enough mass to exceed the limit are the primary source of iron in the cosmos, and iron in the cosmos is ultimately the iron in your blood. But the limit also opened a question. If stars above 1.4 solar masses couldn't become stable white dwarfs, what did they become? The universe had already been answering this question for billions of years. We just had to build the instruments to hear it.
The answer, when it came from space, specifically from X-rays, high-energy light that our atmosphere absorbs entirely and which could only be detected by instruments lifted above the atmosphere on rockets and eventually satellites. In June 1964, a rocket was launched from White Sands Missile Range carrying a set of Geiger counters tuned to detect X-ray photons. It rose above the atmosphere for a few minutes, scanned the sky, and returned its data. Among the sources it detected was a powerful X-ray emitter in the constellation Cygnus. They called it Cygnus X1. Over the following years, as more X-ray observatories reached orbit, culminating in NASA's Uhuru satellite in 1970, the first satellite dedicated entirely to X-ray astronomy, the picture of Cygnus X1 sharpened. The X-ray emission was intense, and it varied. It flickered and fluctuated on timescales of fractions of a second. This variability was deeply informative. Nothing can vary on a timescale shorter than the time it takes light to cross it. This is a fundamental consequence of special relativity. If Cygnus X1's X-ray emission varied on timescales of milliseconds, the emitting region could be no larger than the distance light travels in a millisecond, about 300 kilometers. Whatever was producing all of this X-ray energy was doing so in a region smaller than the state of Montana.
Radio and optical observations eventually pinpointed the position of Cygnus X1 precisely enough to identify its optical counterpart, a bright blue supergiant star called HDE 226868, roughly 6,000 light-years from Earth. This star was orbiting something. Its light was Doppler-shifted periodically, blue-shifted as it moved toward us, red-shifted as it moved away, in a 5.6-day cycle. Something was tugging it around in a tight orbit. That something was invisible. No light came from it. But by measuring the orbital parameters precisely, the period, the velocity, the star's own mass estimated from its spectral type, astronomers could calculate the mass of the invisible companion. Roughly 15 times the mass of the Sun. Too massive to be a neutron star, the other compact object known at the time. Neutron stars have a maximum mass of roughly 2 to 3 solar masses. Above that, not even the pressure of tightly packed neutrons can resist gravity. 15 solar masses was far beyond any possible neutron star. And the geometry made sense. The best model for Cygnus X1 was a black hole orbiting the blue supergiant, pulling gas from the supergiant's outer atmosphere through a process of mass transfer, that gas spiraling down into an accretion disk around the black hole, heating to millions of degrees through friction and compression, and glowing with the X-ray brilliance that had been detected from space. A black hole, 15 times the mass of our Sun. Real, physical, measurable. Stephen Hawking bet against it. He and Kip Thorne made a formal wager, Hawking betting that Cygnus X1 was not a black hole, Thorne betting that it was. Hawking later explained the bet as a kind of insurance. He had spent so much of his career developing the mathematics of black holes that he wanted something to show for his efforts if they turned out to be imaginary objects. The bet provided a small consolation prize. By 1990, the evidence was irrefutable. Hawking conceded. He signed the relevant page in a copy of Brief History of Time and noted cheerfully that he had lost. But Cygnus X1, remarkable as it was only the beginning. It was a stellar mass black hole, a remnant of a single dead star. The truly astonishing discoveries were happening at a much larger scale, at the centers of galaxies. And to find them, we needed to look inward, toward the heart of our own. The evidence was about to force us to confront an uncomfortable possibility, not just that black holes exist, but that they have been shaping the universe around them since nearly the beginning of time.
The center of the Milky Way galaxy is not somewhere you can visit with your eyes. In the direction of the constellation Sagittarius, low in the southern summer sky for observers in the northern hemisphere, never particularly high above the horizon, the galactic center lies 26,000 light-years away, behind curtains of gas and dust so thick that visible light from that region is absorbed and scattered 1 trillion times over before it could ever reach us. You can stare directly toward the galactic center with the finest optical telescope ever built and see nothing. The dust absorbs the light completely. But longer wavelengths of light, radio waves, infrared radiation, are less easily scattered by dust particles. They can penetrate the intervening clouds and emerge still carrying information about their source. And beginning in the 1990s, astronomers learned to take advantage of this penetrating power. 2 teams, working on different continents with different instruments, began pointing their infrared cameras toward the galactic center with a singular goal: to watch, to take image after image, year after year, and see how things moved. At the W.M. Keck Observatory on the summit of Mauna Kea, Hawaii, at an altitude of 4,200 meters, above much of the atmosphere's water vapor and turbulence, astronomer Andrea Ghez and her team at UCLA began their program in 1995.
They used an infrared camera behind a system of adaptive optics, a technology that uses a deformable mirror adjusted thousands of times per second to counteract the blurring effect of atmospheric turbulence and achieve images nearly as sharp as if the telescope were in space. In the Atacama Desert of Chile, at the European Southern Observatory's Very Large Telescope Array, 4 8.2-meter mirrors operating in concert among the most powerful optical infrared telescopes ever built, Reinhard Genzel and his team at the Max Planck Institute for Extraterrestrial Physics were doing the same thing. Different telescope, different team, same patch of sky. What both teams found and continued to find over the following years and decades was a cluster of stars unlike anything in the outer regions of the galaxy. Dozens of bright, young, massive stars orbiting in the immediate vicinity of the galactic center, moving at speeds that grew higher the closer they were to a particular invisible point. Not a visible point, not a star, not anything detectable by any instrument they had. Just a point in space that these stars were clearly orbiting. Stars don't just orbit empty space. Something had to be there. Over time, as the orbital data accumulated, individual stellar orbits became clear. The most famous of these is the star designated S2, sometimes called S02 in the UCLA designation scheme. S2 is a blue star roughly 15 times the mass of the Sun and about 5 times its radius, and it completes one full orbit around the galactic center every 16 years. 16 years! Compare this to our Sun, which takes approximately 225 million years to complete one orbit of the galaxy. S2 does it in 16. At its closest approach, what astronomers call periapsis, S2 passes within roughly 120 astronomical units of the central dark object. 1 astronomical unit is the distance from the Earth to the Sun. S2 swoops to within 120 Earth-Sun distances of whatever is at the center. At that point, its orbital velocity peaks at approximately 7,700 kilometers per second, nearly 3% of the speed of light. A star moving at 3% of the speed of light, flung through space by something invisible. The orbit of S2 is not just a curiosity, it is a precision measuring instrument. Kepler's laws and Newtonian gravity, confirmed by Einstein's general relativity to extraordinary precision, allow astronomers to calculate exactly what mass must sit at the center of any given orbit to produce the observed period and velocity. For S2's orbit, the answer is unambiguous: approximately 4 million solar masses. 4 million times the mass of our Sun, all of it confined to a region of space smaller than our solar system. The orbital precision of S2 and other stars places an upper limit on the physical extent of the central mass, and that limit is small. Small enough that no known configuration of ordinary matter could be that massive in that volume. Except one: a supermassive black hole. 4 million solar masses sitting at the center of the Milky Way. Sitting there right now, as you read this or listen to this, 26,000 light-years away in the direction of Sagittarius. It has a name: Sagittarius A star. Written SGR*, indicating that it is a source of radio emission, one of the original designations before its true nature was understood. It was identified as a compact radio source in 1974 by Bruce Ballack and Robert Brown, working with the Green Bank Telescope in West Virginia. It took 2 more decades of infrared stellar orbit observations to establish that this radio source was a supermassive black hole rather than some other exotic object. Andrea Ghez and Reinhard Genzel, for their roles in establishing this beyond reasonable doubt, shared the Nobel Prize in Physics in 2020. The prize citation noted that their discovery of SGR A star represented the most convincing evidence yet of a supermassive black hole at the center of the Milky Way. Think about what it means that this thing is there, right now, as you go about your day, as the planet turns, as the Sun makes its slow progress through the galaxy.
At the center of everything within 50,000 light-years of you in any direction, there is a point of no return, a place where space-time curves so severely that even light cannot escape. A mass 4 million times greater than our Sun, compressed into a volume smaller than the orbit of Mercury. It has been there for most of the galaxy's history. Stars have formed, lived, and died while it sat there. Civilizations, if any existed, have risen and fallen on worlds we cannot see while it sat there. The 26,000 years of travel time means we see it as it was when humans were painting cave walls in Ice Age Europe. Whatever it is doing right now, we won't know for 26,000 years. But the evidence forces an immediate question. If our galaxy has a supermassive black hole at its center, what about every other galaxy? And the answer to that question, when we gathered it, changed everything.
By the early 2000s, the evidence for supermassive black holes at the centers of nearby galaxies was overwhelming. Galaxy after galaxy, examined with the Hubble Space Telescope and ground-based instruments, revealed the same signature: stars and gas moving too fast near the center to be explained by any ordinary concentration of mass. Always the same pattern, always implying a dark, compact, extraordinarily massive object at the core. The question that remained was whether these objects truly were black holes in the precise sense, whether they truly had event horizons, the one-way membranes that general relativity predicts, or whether they were some other kind of compact, massive, dark object that our theories hadn't yet imagined. Some physicists speculated about massive dark objects, or quasi-black holes, or other exotic configurations. The evidence for extreme mass in a small volume was clear. The evidence for actual event horizons was indirect. Then, a group of astronomers began to think about whether an event horizon could be directly imaged. The idea was audacious. The angular resolution required to image the event horizon of even the largest and nearest supermassive black holes, SGR-A star in our galaxy and M87 star in the Virgo cluster, was extraordinarily demanding. The apparent size of SGR-A star's event horizon, as seen from Earth, is roughly 50 micro-arcseconds. An arcsecond is 1/3600th of a degree. A micro-arcsecond is a millionth of that. 50 micro-arcseconds is the angle subtended by a golf ball on the surface of the Moon as seen from Earth. No single telescope could achieve this resolution, but a technique called Very Long Baseline Interferometry, VLBI, allows multiple telescopes separated by large distances to be combined into a virtual instrument whose effective resolution is determined by the separation between the telescopes rather than the size of any individual dish. The resolution scales with the distance between telescopes divided by the wavelength of observation. To resolve something as small as a black hole shadow, you needed the largest possible baseline, the diameter of Earth itself, and the shortest possible wavelength practical for radio astronomy. The team settled on 1.3 millimeters. At this wavelength, with baselines up to 12,000 kilometers, the theoretical resolution was sufficient. The Event Horizon collaboration, eventually encompassing over 200 scientists from 59 institutions across 20 countries, spent years coordinating observations, developing analysis techniques, and working out the formidable technical challenges of synchronizing telescope arrays on 5 continents using hydrogen maser atomic clocks accurate to a trillionth of a second. Their first target was not SGR-A star, but M87 star, the supermassive black hole at the center of the giant elliptical galaxy Messier 87, 55 million light-years from Earth. They chose M87 star partly because its enormous mass, 6.5 billion solar masses, compared to SGR-A star's 4 million, meant that its event horizon was physically much larger and subtended a comparable angular size on the sky.
But more importantly, M87 star is less variable. The gas around SGR-A star moves so fast, completing orbits in minutes, that the source changes dramatically over the course of a long observation. M87 star's accretion timescale is weeks or months, making it easier to build up a stable image. Observations were conducted in April 2017 during a week-long window when weather conditions at multiple sites were acceptable. Over 4 petabytes of data were collected across 8 telescope sites: South Pole Telescope, ALMA in Chile, APEX in Chile, the IRAM 30-meter telescope in Spain, the James Clerk Maxwell Telescope in Hawaii, the Sub-Millimeter Array in Hawaii, the Sub-Millimeter Telescope in Arizona, and the Large Millimeter Telescope in Mexico. The data was stored on hard drives and flown to processing centers because no network in the world could transmit 4 petabytes in a reasonable time. 2 years of analysis followed. Multiple independent imaging teams using different algorithms and different assumptions, all converging on the same result. On April 10, 2019, at simultaneous press conferences in Washington, D.C., Brussels, Santiago, Shanghai, Taipei, and Tokyo, the image was released. A ring of orange-red emission, a bright crescent brighter on one side than the other, a consequence of the relativistic motion of gas in the accretion disk, which is brighter on the side moving toward us due to Doppler boosting. And at the center, a circular dark region, the shadow of the event horizon, the region where no light escapes, surrounded by the glowing ring of photons that have been bent into near-circular orbits by the extreme space-time curvature near the black hole. The shadow was precisely the size and shape that general relativity predicted for a 6.5 billion solar mass black hole. The bright crescent was on the correct side. The asymmetry of brightness was correct. Every feature of the image matched the predictions of equations that had been written down and largely confirmed in other contexts over the previous century. This was not just a pretty picture. This was a test of general relativity in the regime of extreme gravity, space-time curvature billions of times stronger than anything in our solar system, and general relativity passed with extraordinary precision. 3 years later, in May 2022, the collaboration released the image of SGR-A star, our own black hole. Imaging it was harder. The variability problem required new computational techniques, including machine learning algorithms trained on thousands of simulated black hole images. But the result was equally striking: a ring, a shadow, the event horizon of the object 4 million times the mass of our Sun that has sat at the center of the Milky Way for billions of years, finally seen. Both images, both confirming beyond any reasonable doubt that these are real objects, that the mathematics is right, that Schwarzschild's solution, derived in a trench in 1916, describes real features of the actual universe. It took humanity more than 230 years to get from John Mitchell's thought experiment in a Yorkshire rectory to an actual photograph of a black hole's shadow. But we got there.
There is a second way to observe black holes, radically different from any form of light-based astronomy, not by collecting photons, but by feeling the tremors left in the fabric of space-time by the most violent events in the universe. Einstein's general relativity predicts that when massive objects accelerate, and particularly when they orbit each other, each continuously accelerating toward the other in a gravitational dance, they should generate ripples in space-time, propagating outward at the speed of light. These ripples, called gravitational waves, would alternately stretch and compress space in directions perpendicular to their propagation, the way a water wave alternately raises and lowers the surface of the sea. Einstein predicted gravitational waves mathematically in 1916. He doubted for most of his career that they would ever be detectable.
the effect for any source accessible to human observation would be extraordinarily small. A gravitational wave from a massive astrophysical event crossing Earth would stretch and compress the entire planet by a distance smaller than 1/10,000th the diameter of a proton. Detecting such a displacement would require an instrument of almost incomprehensible precision. But some physicists believed it could be done. Kip Thorne at Caltech and Rainer Weiss at MIT spent decades developing the concept and then the hardware for the Laser Interferometer Gravitational Wave Observatory, LIGO. An L-shaped instrument with arms 4 kilometers long, down which laser beams are sent, reflected off mirrors at the ends, and recombined. When a gravitational wave passes, one arm stretches while the other compresses, and the recombined beams shift out of alignment by an infinitesimal amount that can be measured by observing the interference pattern. The sensitivity required is staggering. LIGO needs to detect displacements of 10 to the minus 18 meters, 1 attometer, or about 1,000th the diameter of a proton. To eliminate noise, the mirrors are suspended on multiple layers of vibration isolation. The laser light circulates hundreds of times within each arm, amplifying the tiny phase shift into something detectable. Every conceivable source of interference, ground vibrations, ocean waves striking distant coastlines, trucks on nearby roads, even quantum fluctuations in the photon number, must be characterized, modeled, and either eliminated or corrected for. LIGO's advanced, upgraded version came online in September 2015. Scientists expected to wait months or years before detecting a signal, assuming their calculations about detection rates were correct. They waited 16 days. On September 14, 2015, at 5:51 a.m. Eastern Daylight Time, the detector at Livingston, Louisiana, registered a signal. 7 milliseconds later, the time it takes a signal traveling at the speed of light to cross the distance between the two detectors, the Hanford, Washington detector registered the same signal. When the waveform was analyzed and converted to sound within the frequency range of human hearing, it produced a brief rising chirp, 2 notes, climbing in pitch over about 0.2 seconds, then stopping. You can find this sound online. It has been described as the most important sound in the history of science. It had been traveling toward us for 1.3 billion years. It was generated when the universe was about 12.5 billion years old, long before the solar system existed. It was generated by 2 black holes, one approximately 36 solar masses, one approximately 29 solar masses, that had been spiraling toward each other for billions of years, radiating away orbital energy as gravitational waves, until in their final seconds they were orbiting each other at hundreds of times per second, moving at a significant fraction of the speed of light. They merged, and in the merger, 3 solar masses of matter was converted entirely into gravitational wave energy in a fraction of a second, not into light, not into heat, not into any form of electromagnetic radiation, into ripples in space-time. The power of this burst exceeded the combined electromagnetic luminosity of every star in the observable universe, every star, every galaxy, everything. For that fraction of a second, this single event outshone the entire rest of the visible cosmos in gravitational wave energy. And the signal that reached us was a displacement of 10 to the minus 18 meters, 1 attometer. We built an instrument that could detect it. Rainer Weiss, Barry Barish, and Kip Thorne received the Nobel Prize in Physics in 2017 for this achievement. Since that first detection, designated GW 150914, LIGO and its European partner Virgo have detected dozens of additional gravitational wave events, black hole mergers of various masses, neutron star mergers, and events mixing both types. Every detection is a new data point about how black holes are distributed in mass, how fast they spin, how often they merge, how they distort space-time as they approach each other. We have opened an entirely new window onto the universe, not a window made of glass that admits light, a window made of space-time that admits gravity. But this represents just one piece of a much larger puzzle.
By the late 1990s, as the catalog of confirmed and candidate supermassive black holes grew into the dozens and then hundreds, something began to emerge from the data that was not predicted by any theory and that no one had really been looking for. A pattern, a relationship, clean, consistent, and holding across every galaxy that had been studied carefully enough. The mass of the supermassive black hole at a galaxy center was proportional to, correlated precisely with, a property of the galaxy called the stellar velocity dispersion of the galactic bulge. The bulge is the central, roughly spherical distribution of old stars surrounding the galactic core. The velocity dispersion is a measure of how fast these stars are moving, not in any particular direction, but in their random thermal motions, the astrophysical equivalent of temperature. Larger velocity dispersion, larger black hole. Every time, in every galaxy studied, across a range of black hole masses spanning 6 orders of magnitude, from a few million solar masses to many billions, the relationship held with remarkable tightness. This is called the M-sigma relation, published in 2000 by Laura Ferrarese and David Merritt, and independently confirmed by Carl Gebhardt and colleagues in the same year. It is one of the most important empirical relationships in modern astrophysics. To appreciate why it is so striking, you need to understand what the velocity dispersion of the stellar bulge actually measures. It measures the gravitational potential of the bulge, the strength of gravity in that region, which is determined by the total mass of the billions of stars in the bulge. The velocity dispersion is a property of the entire galactic bulge, a region that can span thousands of light years. The black hole at the center of that bulge, by contrast, is tiny. SGR-A is 4 million solar masses. The Milky Way's bulge contains something like 10 billion solar masses of stars. The black hole is 0.04% of the bulge mass, 0.04%. Its direct gravitational influence extends perhaps a few hundred light-years at most, the region where the black hole's gravity dominates over the collective gravity of all those billions of stars. The black hole is, in a very real physical sense, irrelevant to the outer bulge. The stars in the outer parts of the bulge have no knowledge of the black hole's mass specifically. They feel only the total gravitational potential of all the mass inside their orbits, most of which is other stars. And yet, the black hole's mass tracks the bulge's velocity dispersion with extraordinary precision. This correlation cannot be coincidence. Two objects that have no direct gravitational communication must nonetheless have evolved in some coordinated way. The growth of the supermassive black hole and the growth of the galactic bulge are linked. They are connected by some process that operates over billions of years and across thousands of light years. The most widely accepted explanation is feedback. When a supermassive black hole is actively accreting, when it is consuming gas and shining as a quasar or an active galactic nucleus, it releases enormous amounts of energy. This energy couples to the surrounding gas of the galaxy, heating it, driving it outward, and suppressing the formation of new stars. As the galaxy tries to grow its bulge, the black hole's activity provides a countervailing force. The system reaches an equilibrium where the black hole's mass is just large enough that its energy output can regulate the galaxy's growth.
The M-sigma relation is the fossil record of this equilibrium. It is written in the masses of billions of stars and the mass of the black hole at their center, a record of a negotiation between gravity and energy that played out over billions of years of cosmic history. But to understand that negotiation in detail, to see how black holes actually managed to control the evolution of their galaxies, we need to go back in time. Back to when these black holes were young and hungry and blazing with the light of trillions of suns.
Because light takes time to travel, we see the universe as it was in the past when we look at distant objects. Every telescope is a time machine. The farther you look, the further back in time you see. When we look at the universe as it existed roughly 10 to 12 billion years ago, back when it was 2 to 4 billion years old, we see something that looks almost nothing like the calm, organized cosmos of today. We see a universe in violent, energetic upheaval, galaxies colliding, star formation proceeding at rates 10 to 100 times higher than today, and scattered across the sky, impossibly bright pinpoints of light. These are quasars. The word comes from quasi-stellar radio source. They were first detected as radio emitters in the 1950s and 1960s, and when their optical counterparts were identified, they looked like stars. But their spectra were bizarre. The spectral lines, the precise wavelengths at which different elements absorb and emit light, were shifted dramatically toward the red end of the spectrum, indicating they were receding from us at enormous velocities. Not velocities produced by individual motion, but the cosmic expansion itself, carrying these objects away from us as space itself stretched. They were at cosmological distances, billions of light years away. And at those distances, their apparent brightness implied luminosities that seemed impossible. A single quasar can outshine an entire galaxy of 400 billion stars by a factor of 100. Some of the most powerful quasars ever detected pour out energy equivalent to tens of trillions of suns, all from a region of space smaller than our solar system. What could possibly generate that much energy in that small a volume? The answer, worked out through the 1960s and 1970s by a series of physicists, including Yakov Zeldovich, Edwin Salpeter, and especially Donald Lynden-Bell, was a supermassive black hole in the process of actively accreting enormous quantities of gas. As gas falls toward a supermassive black hole, it carries angular momentum, rotation, that prevents it from falling straight in. Instead, it spirals, flattening into a disk called an accretion disk. In this disk, adjacent rings of gas rotate at different speeds. The inner rings move faster, the outer rings slower. The friction between these rings converts kinetic energy to heat. In the innermost regions, temperatures reach tens of millions of degrees. At these temperatures, the gas radiates intensely across the entire electromagnetic spectrum, from radio waves through visible light through X-rays and gamma rays. A black hole doesn't actually emit this radiation. The radiation comes from the hot gas in the accretion disk outside the event horizon. But it is the black hole's gravity that powers the process, extracting gravitational potential energy from the infalling gas and converting it to radiation. The efficiency is extraordinary. A black hole accretion disk can convert roughly 10% of the rest mass energy of infalling matter directly to radiation, 10 times more efficient than the nuclear fusion reactions that power stars. This is why quasars shine so brightly. They are the most efficient power plants in the universe, gravity doing work on gas to produce light. And in the early universe, they were everywhere. The most distant quasar currently known, J03181806, was observed as it existed just 670 million years after the Big Bang. Its mass is already 1.6 billion solar masses. The universe was not yet a 20th of its current age, and this black hole had already grown to contain more mass than 1 billion stars. How did it grow so fast?
The answer is still debated. Black holes need seed masses to start from, whether those seeds were the remnants of the first generation of massive stars or direct collapse black holes formed from clouds of gas that never went through the stellar phase, or some other mechanism. And they need abundant gas supplies and the right conditions to accrete rapidly. The early universe provided all of these. Among the most extraordinary quasars ever studied is J0529-4351, identified in 2024 using archival data and then confirmed with the European Southern Observatory's Very Large Telescope. It lies about 12 billion light-years away, meaning we see it as it existed when the universe was less than 2 billion years old. Its luminosity is approximately 500 trillion times that of the Sun. It is accreting mass at a rate of roughly 370 solar masses per year, about 1 solar mass per day. Every day, 1 star's worth of mass swallowed, heated to millions of degrees in the accretion disk, radiated as light and X-rays across 12 billion light-years of space to reach our instruments today. But quasars are overwhelmingly absent in the present-day universe. The nearby universe, the universe of the last few billion years, is almost entirely quasar-free. The supermassive black holes that powered the great quasar epoch of early cosmic history are still there, still sitting at the centers of their galaxies, but they have gone quiet. The gas supplies have been exhausted or expelled or heated to the point where they can no longer fall in at quasar-level rates. Why? What shut them down? The answer is themselves.
In the late 1990s and early 2000s, as computational power increased and cosmological simulations grew more sophisticated, astronomers ran into a systematic problem that proved surprisingly difficult to resolve. Their simulations of galaxy formation, of how gas cooled and collapsed within dark matter halos, and how stars formed from that gas, were producing a universe that didn't look like the one we live in. Specifically, they were producing too many very massive galaxies. In the simulated universe, gas in the most massive dark matter halos could cool and collapse efficiently, forming stars without limit. The result was a population of enormous galaxies, far more numerous than anything we actually observe. In the real universe, there are relatively few truly massive galaxies. The most massive galaxies, systems containing 1 trillion or more solar masses and stars, are rare. And crucially, the most massive galaxies appear to have stopped forming stars long ago, billions of years in the past. They are red and dead, populations of old red stars with no ongoing star formation. Something shut off star formation in these galaxies and kept it off. In lower mass simulations, the culprit was identified as supernova feedback, the energy from exploding stars, which could heat and expel gas from smaller galaxies. But in the most massive galaxies, supernova feedback was insufficient. The galaxies were too deep in their gravitational wells. Supernovae couldn't do enough. The missing ingredient was identified as the supermassive black holes. When those were included, when the simulations modeled the energy output of actively accreting black holes and how that energy coupled to the surrounding gas, everything changed. The distribution of galaxy masses matched observations. The quenching of star formation in massive galaxies was reproduced. The relationship between black hole mass and bulge mass emerged naturally from the dynamics. AGN feedback, active galactic nucleus feedback, the injection of energy by accreting supermassive black holes, is now considered a fundamental and non-negotiable ingredient in any realistic model of galaxy formation and evolution. The mechanism works on multiple scales and through multiple channels. In the most powerful mode, called quasar mode or radiative mode feedback, the quasar-level luminosity of a rapidly accreting black hole drives winds of gas outward from the accretion disk at thousands of kilometers per second.
These winds can sweep through the host galaxy, heating and expelling the cold gas reservoirs that would otherwise collapse into new stars. Observations with X-ray and optical telescopes have detected these winds directly in many nearby active galaxies, molecular and atomic gas moving outward at speeds implying energies of billions of solar masses over the lifetimes of the outflows. In a second mode, called jet mode or maintenance mode feedback, even a weakly accreting black hole, one not bright enough to be called a quasar, can launch collimated jets of relativistic plasma that carry enormous mechanical power into the surrounding gas. These jets inflate cavities in the hot gas halos surrounding massive galaxies and galaxy clusters, driving sound waves and turbulence that keep the gas hot and prevent it from cooling and forming stars. The evidence for jet mode feedback from NASA's Chandra X-ray Observatory is among the most visually striking in all of astrophysics. In observations of the Perseus galaxy cluster, 240 million light-years away, Chandra revealed the hot X-ray emitting gas of the cluster to be filled with an extraordinarily complex structure of cavities, ripples, and filaments, all centered on the central galaxy NGC 1275 and its active supermassive black hole. The cavities are holes blown in the cluster gas by the jets from the black hole, regions where the plasma from the jets has pushed the hot gas aside, creating bubbles millions of light-years across. These bubbles rise buoyantly through the surrounding gas like hot air balloons, carrying energy outward and distributing it throughout the cluster. The ripples are pressure waves, sound waves propagating outward from the black hole at the speed of sound in the cluster gas, which at tens of millions of degrees is about 1,000 kilometers per second. The Chandra team calculated the frequency of these sound waves, 57 octaves below middle C, a note so deep and so vast that no instrument could play it, no ear could hear it, no physical medium on Earth could carry it, and yet it rings continuously through the hot gas of Perseus, a cosmic organ sustained by a black hole. The energy being pumped into the Perseus cluster by its central black hole, integrated over the billion or more years this process has been operating, exceeds 10 to the 61 ergs. That is the energy equivalent of taking 10 billion supernovae and sustaining their output for the entire age of the universe. All of it coming from one black hole, maintaining the temperature of a structure that spans millions of light-years, suppressing the formation of trillions of solar masses of stars that would otherwise have formed from the cooling gas. Consider what this means at the scale of the observable universe. Every massive galaxy cluster, and there are tens of thousands visible to our instruments, contains a central massive galaxy with a supermassive black hole. Every one of these black holes, even when weakly active, is continuously injecting energy into the intercluster gas, maintaining its temperature, shaping the thermal and chemical history of the largest gravitationally bound structures in the universe. The evidence extends far beyond individual galaxies into the cosmic web itself.
So far, everything we have discussed has been about black holes from the outside, the effects they produce on surrounding gas, on stellar orbits, on the large-scale structure of the universe. These are all phenomena accessible to observation, measurable by instruments, testable against prediction. But black holes also have an inner life, a theoretical life, that is every bit as extraordinary as their observable effects. To understand what black holes truly are, at the level of fundamental physics, we need to venture into territory where observation becomes impossible and only mathematics can guide us. The journey begins in 1974 with a result so surprising that it astonished even its discoverer. Stephen Hawking was then at Cambridge, one of the rising stars of British theoretical physics, working on a problem at the intersection of two theories that had never been successfully unified.
General relativity described gravity and space-time. Quantum mechanics described particles and fields at the smallest scales. In the half-century since both theories had been developed, they had each been confirmed to extraordinary precision in their respective domains, and they were mathematically incompatible with each other. The two most successful theories in the history of physics could not both be literally true at the same level, because their mathematical structures conflicted in a regime where both should apply. One regime where both apply simultaneously is near the event horizon of a black hole. The strong gravitational field requires general relativity. The temperatures and particle physics require quantum mechanics. Hawking decided to work out what quantum mechanics implied about fields near an event horizon. The starting point was a concept from quantum field theory. The quantum vacuum is not empty. At every point in space, quantum fields are fluctuating. Virtual particles and antiparticles are continuously being created in pairs, existing for a moment determined by the Heisenberg uncertainty principle, and then annihilating each other and returning their borrowed energy. These virtual pairs are normally undetectable. They appear and vanish so quickly that no instrument can register them directly. Their effects are real and have been measured, the Casimir effect, the Lamb shift, but the particles themselves are not physically real in the sense of being able to travel to a detector and be registered. Near an event horizon, however, something different can happen. When a virtual pair appears very close to the horizon, one particle outside, one particle inside, the particle inside the horizon is causally disconnected from the one outside. They cannot communicate. They cannot annihilate each other as they normally would. Instead, the particle outside escapes. It becomes a real observable particle, propagating away from the black hole. And the particle that fell in carries negative energy by the accounting of quantum field theory, which means that the total energy of the black hole decreases by the amount carried by the escaping particle. From the perspective of a distant observer, the black hole appears to be emitting particles, thermal particles following a Planck spectrum with a well-defined temperature, as if the black hole were a warm body radiating heat. This is Hawking radiation, and the temperature associated with it, which Hawking derived by careful and intricate calculation, is T equals h bar c cubed divided by 8 pi g mkb, where h bar is the reduced Planck constant, c is the speed of light, g is Newton's gravitational constant, m is the mass of the black hole, and kb is Boltzmann's constant. Notice the m in the denominator. The temperature is inversely proportional to the mass. A more massive black hole is cooler. A less massive one is hotter. For a stellar mass black hole of 1 solar mass, this temperature is approximately 60 nanokelvins, 60 billionths of a degree above absolute zero. The cosmic microwave background radiation filling the universe today has a temperature of about 2.7 kelvins, more than 40 million times hotter. For any black hole that currently exists in the universe, Hawking radiation is completely swamped by the background radiation, undetectable by any instrument we can build or imagine building. But the implication is profound, and it operates over timescales that dwarf the current age of the universe. As a black hole radiates, it loses mass. As it loses mass, its temperature rises. Remember, smaller mass means higher temperature. Higher temperature means more intense radiation. More intense radiation means faster mass loss. The process accelerates. A black hole with the mass of the Sun would lose energy at an initial rate so slow that it would take approximately 2 × 10⁻⁶ years to evaporate completely. That is 2 followed by 67 zeros, years. The current age of the universe is 1.4 × 10⁻⁻⁰ years, 10 billion years. The evaporation time is longer by a factor of more than 10 to the 57th, 10 million trillion 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 times the current age of the universe. Supermassive black holes evaporate even slower. A black hole of 1 billion solar masses would take roughly 10 to the 90th years to evaporate completely. A black hole of 10 billion solar masses, comparable to the largest known, would take around 10 to the 100th years. But eventually, they all evaporate. Every black hole that forms anywhere in the universe will, in the unimaginably distant future, radiate away the last of its mass in a brief flash of Hawking radiation and cease to exist. Hawking announced this result in a paper in 1974. The reaction from the physics community was initially skeptical. The result was too surprising, too counterintuitive. John Wheeler, who had coined the term black hole, reportedly said when he first heard it that the result was impossible. But the mathematical derivation was airtight, and over the following months, physicists who checked it found no errors. The result stood, and it immediately generated a crisis.
Quantum mechanics is founded on a bedrock principle, not a detail, not an approximation, not a result valid only under certain conditions, a foundational axiom without which the entire theoretical structure collapses. That principle is unitarity. The quantum mechanical evolution of a closed system is reversible. If you know the exact quantum state of a system at any moment in time, you can, in principle, calculate its exact quantum state at any other moment, past or future. The Schrödinger equation, which governs quantum evolution, is time reversible. Information about the past is always recoverable from the present state of the system. Information is never created or destroyed. This is not a mere mathematical technicality. It is the reason quantum mechanics can make predictions at all. It is why quantum computers, which operate on the principle of quantum coherence and unitarity, can solve certain problems exponentially faster than classical computers. Remove unitarity, and quantum mechanics becomes not just inaccurate, but incoherent. Now consider a black hole. Matter falls in, ordinary matter carrying quantum information. Every particle has a quantum state, a precise description of its spin, momentum, position, and all other quantum numbers. This information crosses the event horizon with the matter. It is now inside the black hole. Over time, Hawking radiation carries energy away. Eventually, the black hole evaporates completely. The Hawking radiation, the stream of photons and other particles emitted over the black hole's lifetime, carries the energy away. What does it carry about the quantum information? When Hawking analyzed the radiation, he found that it was, to a very good approximation, thermal, random, like the radiation from a hot object at thermal equilibrium, which carries no detailed information about what the object is made of or what happened to it previously. If you look at the light from a fireplace, you cannot tell from the light alone what kind of wood was burned, or what books were thrown in, or what the furniture looked like before it was fuel. If the Hawking radiation is truly thermal, truly random, then when the black hole evaporates, the quantum information that fell in is gone, not encoded elsewhere, not hidden, gone, destroyed. This violates unitarity, fundamentally, irreparably, and with no obvious way to fix it. This is the black hole information paradox, and it represents one of the deepest unsolved problems in theoretical physics. It is not an observational problem. We cannot observe Hawking radiation from any real black hole. It is a theoretical problem. Our two best theories of the physical world, applied carefully and correctly to a well-defined physical situation, produce logically contradictory results. One says information is preserved, the other says it is destroyed. They cannot both be right. For nearly 3 decades, Hawking argued that information was genuinely destroyed, that black holes were an exception to the principle of unitarity, a place where the most fundamental rule of quantum mechanics simply didn't hold.
This was enormously controversial. Most quantum physicists found the position untenable, a capitulation to inconsistency in our deepest theories. John Preskill at Caltech maintained that information must be preserved. He and Hawking made a formal bet, with Kip Thorne siding with Hawking. The stakes, an encyclopedia chosen by the winner. The debate came to a head in 2004 when Hawking gave a public lecture in Dublin at the GR17 conference, the International Conference on General Relativity and Gravitation, and announced, to enormous media attention and considerable surprise among his colleagues, that he had changed his mind. He now believed information was preserved, that it escaped the black hole encoded in subtle, essentially undetectable correlations in the Hawking radiation. He presented Preskill with a baseball encyclopedia. Information about the past is available if you know how to look, he reportedly said. But the mechanism, how exactly the information gets out and what happens to it inside the black hole, remained mysterious. Hawking's concession was intuition, not calculation. The calculation came later. In 2019, a series of papers involving, among others, Ahmed Almeri at the Institute for Advanced Study, Netta Engelhardt at MIT, Donald Maroth at UC Santa Barbara, and Henry Maxfield derived what is now called the Page curve for black hole evaporation. Don Page had argued in 1993 that if information is preserved, the entropy of the Hawking radiation should follow a specific trajectory, increasing for the first half of the black hole's life and then decreasing in the second half, returning to zero when the black hole has fully evaporated. This shape, the Page curve, is the signature of unitary, information-preserving evolution. The 2019 papers derived the Page curve from first principles, using insights from the holographic principle and a concept called the quantum extremal surface. The derivation showed that information about the black hole's interior is encoded in the Hawking radiation, not in individual photons, which look thermal, but in the quantum correlations between photons emitted at different times across the entire lifetime of the black hole. This is extraordinarily cold comfort for anyone hoping to recover the information in practice. Decoding those correlations would require performing quantum measurements of arbitrary precision on every photon emitted over 10 to the 67 years, an experimental program that would require instruments larger than the observable universe and operating times longer than the universe's current age multiplied by incomprehensible factors. The information is preserved in principle. It is irrecoverable in practice. But the theoretical resolution of the paradox, or at least this progress toward one, required introducing ideas that have profound implications for how we understand space-time itself. The quantum extremal surface that encodes the black hole's information lies, in a quantum gravitational sense, outside the event horizon, even though in the classical general relativistic sense it appears to be inside. This means that the event horizon, the boundary of the black hole, is not quite what general relativity says it is at the quantum level. The interior of the black hole, in the fully quantum gravitational description, is connected to the exterior radiation in a way that classical physics simply cannot describe. This forces us to reconsider fundamental assumptions about the nature of spacetime, specifically about whether spacetime is a fundamental entity or an emergent one, whether the smooth, continuous, four-dimensional geometry that general relativity describes is the bedrock of reality, or whether it arises from something more primitive, something quantum, something we do not yet have the conceptual vocabulary to fully express. The black hole information paradox is not just a puzzle about what happens to matter that falls into black holes. It is a clue, perhaps the most important clue we have, about the deep structure of space and time.
The instruments that have brought us to our current understanding of black holes represent some of the greatest engineering achievements in human history. The laser interferometers of LIGO, maintaining measurement precision at the scale of 1,000th of a proton's diameter. The Event Horizon Telescope, coordinating 8 telescope arrays across 5 continents with atomic clock precision. The Chandra X-ray Observatory, providing 30-centimeter angular resolution from orbit at X-ray wavelengths that no ground-based telescope could ever access. Each of these instruments required decades of development, billions of dollars of investment, and teams of hundreds of scientists and engineers. And yet the people who built them, who work with them daily, who know their limitations most intimately, will tell you without hesitation, these are the first-generation instruments. The discoveries we have made with them are the beginning of the story. The next-generation Event Horizon Telescope, NGEHT, is currently being designed. It will expand the current array with new stations, including potential locations in Africa, Greenland, and the high Andes, and is exploring the possibility of incorporating a space-based receiver in low Earth orbit or at a Lagrange point, which would extend the effective baseline beyond the diameter of Earth itself. With a space component, the effective telescope diameter could be 10,000 kilometers or more, nearly the Earth-Moon distance. The resolution improvement over the current EHT would be transformative. Where today we see M87 star and SGR-A star as blurry rings, the event horizon shadow resolved, but the internal structure of the accretion flow only suggested, the NGEHT would resolve individual features within the accretion disk. We would see the magnetic field structure near the event horizon, which controls how gas flows in and how jets are launched. We would see individual hotspots, concentrations of particularly bright, hot plasma orbiting the black hole, and track their motion around the orbit. For SGR-A star, the angular resolution of the NGEHT would be sufficient to resolve features the size of a large solar system at a distance of 26,000 light-years. We would be watching in real time, or as close to real time as the 26,000-year light travel time permits, the accretion dynamics of the black hole at our galaxy's center. Not a single blurry averaged image, but a movie. LISA, the Laser Interferometer Space Antenna, will be the gravitational wave observatory that transforms our understanding of supermassive black holes. It is scheduled for launch in 2035, built by the European Space Agency with NASA participation, and it will occupy a triangular formation of 3 spacecraft separated by 2.5 million kilometers, trailing Earth in its orbit around the Sun. Laser beams transmitted between the spacecraft will form a gravitational wave interferometer of previously impossible scale. LISA's sensitivity will peak at frequencies far lower than ground-based detectors like LIGO, millionths of a hertz rather than tens of hertz. This is the frequency range of gravitational waves from supermassive black holes, pairs of massive black holes that have come together following galactic mergers and are slowly spiraling toward each other under gravitational radiation losses. When LISA begins operations, it will immediately be sensitive to dozens or hundreds of known and anticipated sources. Supermassive black hole mergers, the most powerful gravitational wave events in the universe, events that can briefly outshine the entire rest of the universe in gravitational wave luminosity, will be detectable across the observable universe. LISA will measure the masses, spins, and orbital parameters of merging supermassive black holes with precision that will allow stringent tests of general relativity in the most extreme gravitational environments that the universe produces. It will also detect extreme mass ratio in spirals, events where a stellar mass object, a white dwarf or neutron star or small black hole, falls slowly in a spiral into a supermassive black hole.
These inspirals last for thousands to millions of orbits before the final merger, and each orbit maps out the geometry of spacetime around the supermassive black hole in extraordinary precision. We will use these spirals as tracers to map the spacetime of supermassive black holes, in the same way that a satellite mapping Earth's gravitational field traces the planet's irregular shape. We will learn whether real supermassive black holes have the exact spacetime geometry predicted by general relativity for a rotating black hole, the Kerr metric, or whether there are deviations that hint at new physics. Meanwhile, the gravitational wave background has already been detected by pulsar timing arrays. In 2023, multiple international collaborations, the North American Nanohertz Observatory for Gravitational Waves, the European Pulsar Timing Array, the Parkes Pulsar Timing Array in Australia, and the Chinese Pulsar Timing Array simultaneously reported evidence for a background of gravitational waves permeating the universe, detected by monitoring the arrival times of radio pulses from dozens of millisecond pulsars across the sky. Millisecond pulsars are neutron stars spinning hundreds of times per second, emitting beams of radio waves like cosmic lighthouses. They are extraordinarily regular. Some are more stable than atomic clocks over long timescales. By monitoring the arrival times of their pulses over decades, analysts can detect the tiny variations caused by gravitational waves passing through the Milky Way, stretching and compressing the distances between Earth and the pulsars. The 2023 detections showed the characteristic signature of a gravitational wave background, correlated timing variations between pulsars across the sky in a specific pattern predicted by general relativity. The amplitude and frequency of the background is consistent with it being produced by the combined gravitational radiation of billions of supermassive black hole pairs slowly spiraling together in galaxies throughout the universe. We are now listening to the gravitational hum of supermassive black holes throughout cosmic history. Every merger that has happened in the billion-year history of galaxy formation has contributed to this background, and by analyzing its spectrum, the distribution of gravitational power across frequencies, we can infer how often supermassive black holes merge, how long they take to spiral together after their galaxies collide, and how they grow over cosmic time. The era of gravitational wave astronomy is barely a decade old. LISA will expand it by orders of magnitude in sensitivity and frequency range. Within the lifetimes of most people reading this, we will have a complete census of supermassive black hole mergers across the observable universe.
Sag-A, we said earlier, is quiet. Compared to the blazing quasars of the early universe, it is nearly dormant, accreting at a rate billions of times lower than the most active black holes we know of. It is, by the standards of active galactic nuclei, barely active at all. Barely is not the same as not. In April 2019, the same week the Event Horizon Telescope released the first image of M87 star, astronomers at the Keck Observatory in Hawaii and at the European Southern Observatory's Very Large Telescope in Chile were monitoring Sag-A in the near-infrared as part of ongoing programs tracking its variability. What they saw, beginning on the night of May 13th, was something unprecedented in over 20 years of continuous monitoring. Sag-A flared. Its near-infrared brightness increased by a factor of approximately 75 over its typical value, the brightest flare ever recorded from our galactic center in that wavelength range. The flare rose over the course of about an hour, peaked, and then declined. While at peak, Sag-A was temporarily the brightest object in the near-infrared sky of the galactic center region, outshining stars that had been quiescent for as long as anyone had been watching. The physical cause of the flare is not definitively established.
The leading hypotheses involve the disruption of an asteroid or small body by Sag-A's tidal forces, or the orbital perturbation of gas streams near the black hole by the passage of a nearby stellar mass, possibly related to the G2 cloud, a gas cloud that made a close approach to Sag-A in 2014. Whatever the cause, the flare was a reminder that even our quiet black hole is not truly quiescent. It feeds in small bursts continuously. But the evidence for much more dramatic past activity extends across the entire galaxy. The Fermi bubbles were discovered in November 2010 by Meng Su, Tracy Slatier, and Douglas Finkbeiner, using data from NASA's Fermi Gamma Ray Space Telescope. When the team removed the diffuse gamma-ray background from the Fermi sky map, they found something astonishing. Two enormous lobes of gamma-ray emission extending symmetrically above and below the plane of the Milky Way, each about 25,000 light-years in height and centered precisely on the galactic center. The bubbles were huge. Together, they span half the visible extent of the Milky Way as seen from outside. They were hot. The gas within them was at temperatures of millions of degrees, producing hard X-ray and gamma-ray emission. They were sharp-edged. The boundary between the bubble interiors and the surrounding gas was crisp, not diffuse, suggesting they had expanded faster than the surrounding gas could respond. And they were recent, to astrophysical standards at least. The estimates for when the event that inflated them occurred range from about 2 million to about 8 million years ago. 2 to 8 million years is an eye blink in cosmic time. What could produce such structures? The two main hypotheses are a major starburst, a rapid episode of intense star formation in the galactic center, producing numerous supernovae that collectively drove a massive outflow, and a period of dramatically enhanced AGN activity by Sag-A itself. Current evidence leans toward AGN activity as the primary driver, possibly combined with starburst contribution. If Sag-A was responsible for the Fermi bubbles, then approximately 2 to 4 million years ago, our galaxy's central black hole went through a period of activity vastly greater than anything observed today. Not quasar-level activity, not remotely, but active enough to launch jets or winds energetic enough to inflate two 25,000 light-year lobes of hot gas above and below the galactic plane. 2 to 4 million years ago, Australopithecus africanus was walking the savanna of eastern Africa. Homo habilis was beginning to shape stone tools. The first members of our genus, Homo, were living in Africa and beginning to show signs of the cognitive sophistication that would eventually lead to civilization. And the black hole at the center of our galaxy was erupting. No one then had the mathematics to understand it. No one then had eyes sensitive to X-rays or gamma rays. They saw a night sky much like the one we see today, perhaps slightly different in the positions of the constellations. Stellar proper motions accumulate over millions of years, but otherwise familiar. We will never know if they noticed anything unusual in the sky. They left no record that we can interpret on that level. But the black hole's eruption is recorded in the structure of our galaxy, in the two enormous lobes of hot gas that we can now see 26,000 years later as they continue to expand slowly outward. In the gas that was heated, the star formation that was suppressed, the energetic particles that were accelerated into the galactic halo. Our own past is written in fire that we can now, finally, read.
The question of what black holes mean for us, for humanity, for life, for the conditions that allowed our existence, is not a question usually asked in the formal language of astrophysics, but it is one that the data now compels us to take seriously. Consider the elements in your body. The hydrogen in your water and your DNA is primordial, created in the first 3 minutes after the Big Bang, the simplest atom, 1 proton and 1 electron. It has been hydrogen for 13.8 billion years, passing through gas clouds and stars and interstellar space and oceans before becoming part of you. But the heavier elements, the carbon in your DNA, the nitrogen in your proteins, the oxygen you breathe, the phosphorus in your cell membranes, the calcium in your bones, the iron in your blood, none of these were made in the Big Bang. They were all forged in stars. Stars that lived, burned through their nuclear fuel, and died in explosions that scattered their manufactured elements into the interstellar medium. The explosions that created the oxygen in your lungs were supernovae, the same supernovae that leave behind neutron stars and black holes. The iron in your blood came from type 1a supernovae, white dwarfs that exceeded the Chandrasekhar limit and detonated completely, the same Chandrasekhar limit whose discovery Eddington tried to suppress. The heaviest elements, gold, platinum, uranium, came from neutron star mergers, the same events detected by LIGO as gravitational wave sources. You are assembled from the debris of cosmic violence, from the explosions of stars and the mergers of neutron stars, from events that formed black holes as their afterthoughts. Now consider the galaxy itself. The Milky Way has been forming stars for roughly 12 billion years at rates that have varied with time, higher in the past, lower now. The pace of that star formation was regulated by AGN feedback from SGRA star. As SGRA star was more active, as it was during its quasar-like youth, and perhaps during the episode that inflated the Fermi bubbles, it heated and expelled gas that would otherwise have formed stars. This regulation kept the Milky Way from consuming its gas reservoir too quickly. It maintained star formation at a sustainable rate for long enough that second and third and fourth generations of stars could form. Stars enriched by the elements from previous stellar generations, stars with the metallicity to form rocky planets, stars that live long enough to allow those planets to develop complex chemistry and eventually life. The rate of star formation that allowed our Sun to form 4.6 billion years ago from gas already enriched by earlier generations of stars in a galaxy that had maintained a stable environment for billions of years, this was regulated in part by the black hole at our galaxy's center. More broadly, the large-scale structure of the universe, the cosmic web of filaments and voids, the distribution of galaxy sizes and masses, the thermal state of the intergalactic medium, all bear the fingerprints of AGN feedback operating across cosmic time. The universe looks the way it does in its large-scale organization, partly because black holes have been regulating it since the first galaxies formed. We exist in a very meaningful sense in a universe shaped by black holes. The conditions for our existence, the elements in our bodies, the stability of our galaxy, the organization of the cosmos around us, were made possible, at least in part, by the most extreme objects in the universe.
Throughout this journey, we have maintained a careful observational distance. We have discussed what black holes do to space-time around them, what they do to galaxies, what they do to the large-scale structure of the universe. We have approached the event horizon in our instruments and our mathematics, but we have always stayed outside. Now we step closer, not physically. No instrument we can build will ever send information back from inside an event horizon, but theoretically, mathematically, with the full force of the best physical theories we have, we ask, what is in there? General relativity gives an answer. It gives it with confident mathematics and no apology for its extreme conclusions.
Inside the event horizon, space-time has a character that is fundamentally different from the space-time we inhabit. In ordinary space-time, time flows in one direction, the future, and you have freedom in which spatial direction to move. You can go left or right, forward or backward, up or down. Space is the domain of freedom. Time flows whether you want it to or not. Inside a black hole, in the mathematical description of general relativity, this relationship is inverted. The radial coordinate, the coordinate pointing toward the singularity, takes on the character of a time coordinate. It becomes the future. You have no more freedom to avoid moving toward the singularity than you have freedom in ordinary space-time to avoid moving toward the future. You can choose what to do with your spatial directions, but you cannot stop moving toward the center. Time carries you there. And at the center, for a non-rotating black hole, a Schwarzschild black hole, there is the singularity, a point in mathematical terms, a moment in time, a place where the curvature of space-time becomes infinite, where the tidal forces, the differences in gravitational pull across the extended body of any infalling object, become infinite, where the density of any infalling matter becomes infinite. In practice, this means that anything falling into a black hole will eventually encounter a moment when it is compressed and stretched without limit. The equations say infinite density, infinite curvature, infinite tidal force, all at one moment. And then, nothing. The equations stop. The coordinates no longer produce meaningful numbers. The mathematical description of space-time ceases to be defined. This is the singularity, and virtually every physicist who has thought carefully about it believes it is not real, that it is an artifact of the limitations of general relativity rather than an actual physical feature of the universe. Infinite values in physical equations are almost always a sign of theoretical breakdown, not physical reality. When Newton's equations produce infinite force at zero distance between point masses, we don't conclude that infinite forces exist. We conclude that point masses are an idealization that breaks down at short distances, and that a better theory, quantum mechanics, quantum field theory, gives finite answers. Similarly, the singularity inside a black hole almost certainly does not represent infinite density in any physical sense. It represents the point where general relativity exceeds its domain of validity and must be replaced by a more complete theory. What would that theory predict? We do not know. We do not have the theory, but we have candidate theories, and they make different predictions, each striking in its own right. In loop quantum gravity, developed over decades by Abhay Ashtekar, Lee Smolin, Carlo Rovelli, and many others, space-time itself is discrete at the Planck scale, 1.6 times 10 to the minus 35th meters. Not a continuous smooth manifold, but a network of discrete quanta of geometry, woven together into the space-time fabric we experience at larger scales. The Planck scale is so small that 10 to the 20 Planck lengths fit within a proton's diameter. No current or foreseeable experiment can probe physics at this scale directly. But mathematically, this discrete structure changes the behavior of matter at extreme densities.
In loop quantum cosmology, the application of loop quantum gravity to the entire universe, the Big Bang singularity is replaced by a big bounce. The preceding universe, which may have been contracting, reached a minimum volume determined by the quantum of geometry and then rebounded into the expanding universe we inhabit. The Big Bang was not a creation event, but a transition. Applied to black hole interiors, loop quantum gravity predicts an analogous bounce. The collapsing matter, compressed to Planck density, reaches a minimum volume and then rebounds, potentially expanding into a new region of spacetime. not into our universe, into a new, causally disconnected spacetime, a new universe with its own structure, expanding and evolving independently of ours. This is cosmological fecundity, the idea that black holes are the birth events of new universes, and we will return to it shortly. In string theory, the most developed of the quantum gravity programs, and one that has generated an extraordinary amount of mathematical physics, fundamental objects are one-dimensional strings vibrating at different frequencies, with the different vibrational modes corresponding to different particle types. Space and time may have more dimensions than the 4 we experience, with the additional dimensions compactified, curled up at scales too small to detect. The extended nature of strings means they cannot be localized to a mathematical point, which provides a natural regulator of the singularity. In various string theory models, the interior of a black hole may be described by exotic geometries involving extra dimensions, branes, higher dimensional analogs of strings, and other structures that have no analog in classical physics. The singularity is replaced by some finite curvature structure, though the precise nature of this structure depends on details of the compactification and remains an active area of research. Most provocatively, in 2012, a team of physicists, Ahmed Almeri, Donald Maroff, Joseph Polchinski, and James Sully, known from their initials as AMPS, published a paper that struck at the heart of what we thought we knew about the experience of crossing an event horizon. General relativity predicts that an observer falling into a massive enough black hole experiences nothing unusual at the moment of crossing the event horizon. The space-time curvature there is gentle. For a billion solar mass black hole, the tidal forces at the horizon are no stronger than those you feel from Earth's gravity here at the planet's surface. The event horizon is defined not by anything locally dramatic, but by the global structure of space-time, by the fact that no future-directed path from within it leads back out. An infalling observer would cross it without knowing, floating in what felt like locally flat space. AMPS showed that this comfortable picture is inconsistent with the quantum mechanical preservation of information. If information is encoded in the Hawking radiation, if the radiation from the black hole is not truly thermal but contains subtle correlations, then the quantum state of the Hawking radiation must be entangled with the quantum state of the material that fell into the black hole. But this entanglement, they argued, violates a principle of quantum mechanics called the monogamy of entanglement. A quantum system cannot be maximally entangled with 2 different systems simultaneously. If the outgoing Hawking radiation is entangled with earlier radiation in the way required for information preservation, it cannot also be smoothly entangled with the infalling material in the way required for a smooth horizon crossing. The resolution they proposed was disturbing. The smooth spacetime at the event horizon predicted by general relativity does not exist. Instead, an infalling observer encounters a firewall, a wall of high-energy radiation at the horizon, generated by the enormous energy density of the entanglement violations required to preserve information outside. Instead of floating serenely through an invisible boundary, the observer is instantly incinerated. The firewall paradox, as it became known, generated an enormous volume of theoretical work. Various escape routes were proposed. Juan Maldacena and Leonard Susskind suggested that the Hawking radiation particles are connected to the black hole interior by microscopic wormholes, the ER equals EPR conjecture, connecting Einstein-Rosen bridges, wormholes, to Einstein-Podolsky-Rosen entanglement. If the escaping radiation and the interior are connected by wormholes rather than by conventional quantum entanglement, the monogamy problem might be avoided. None of these proposals is fully worked out. The firewall paradox and its various proposed resolutions remain live research topics at institutions including the Institute for Advanced Study in Princeton, the Kavli Institute for Theoretical Physics in Santa Barbara, the Perimeter Institute in Canada, and many others around the world. What is clear from all of this theoretical ferment is something both humbling and exciting.
The inside of a black hole is a place where our deepest theories come into genuine conflict, where the most fundamental principles of the two great physical theories of the 20th century cannot both hold simultaneously, where the nature of space and time themselves is most urgently in question. The inside of a black hole may be the place where we most need and most urgently will eventually find the theory of quantum gravity that will transform our understanding of reality at the deepest level.
Let us now travel forward in time, not by years or decades or centuries, not by millions or billions of years, by timescales so vast that the numbers require exponents just to write down in a reasonable space, timescales against which the entire history of the universe to date, all 13.8 billion years of it, is a rounding error. We begin in the relatively near cosmological future, about 5 billion years from now. The Sun will exhaust its hydrogen fuel and swell into a red giant, swallowing Mercury and Venus, and quite possibly Earth, before shedding its outer layers and leaving behind a white dwarf. The Milky Way and Andromeda galaxies, already approaching each other at about 110 kilometers per second, will undergo their first close encounter in about 4.5 billion years and eventually merge into a single large elliptical galaxy over the course of perhaps a billion more years. During this merger, SGR-A star and Andromeda's central black hole, roughly 110 million solar masses, will eventually find each other, form a binary system, and spiral together over millions or billions of years until they merge in a gravitational wave burst that will be, for a few seconds, the most powerful event in the nearby universe. We will not be here to see it. Whether anything else will be is uncertain. Further forward, around 100 trillion years from now, 10 to the 14 years, the last stars will exhaust their fuel. The red dwarfs, the smallest, coolest, most frugal of stars, will be the last to go. They burn so slowly and so efficiently that some of them will still be shining when the universe is 10,000 times its current age. But eventually they too will exhaust their hydrogen, swell, and fade. The universe will enter what cosmologists call the degenerate era. The sky will be dark, no stars will burn, the galaxies will be populated by stellar remnants, white dwarfs cooling through billions of years toward absolute zero, neutron stars spinning down as they radiate away their rotational energy, black holes, stellar mass and supermassive, dominating the gravitational landscape. This era will last until approximately 10 to the 40 years. During this time, the occasional close encounter between stellar remnants may reignite nuclear burning briefly. A white dwarf that accumulates enough mass from a companion might briefly shine as a Type 1a supernova. Two neutron stars might merge in a brief burst of gravitational waves and gamma rays. But these are individual events in an overwhelmingly dark cosmos. The era of starlight is over. By 10 to the 40 years, even the proton, if the proton decays, as some theories of grand unification predict, will have decayed. The atoms in white dwarfs and neutron stars will have dissolved. The stellar remnants themselves will have evaporated into lighter particles. What remains are black holes and a thin gas of electrons, positrons, photons, and neutrinos. This is the black hole era. The universe is dominated, gravitationally and structurally, by black holes. Stellar mass black holes, millions of solar masses each, having grown through occasional mergers. Supermassive black holes, having long since consumed most of what was left in their galaxies, grown through the occasional merger of two black holes that drift close enough for gravitational radiation to draw them together. These black holes are cooling.
Their Hawking temperatures are tiny beyond all practical description. For a solar mass black hole, about 60 nanokelvins. For the remaining supermassive monsters, far colder still. But the radiation is real. Each quantum process near each event horizon is, over unimaginable timescales, draining mass from the black hole. The stellar mass black holes go first. A black hole of one solar mass evaporates in about 2 × 10⁻�67 years. Over this timescale, it loses mass continuously, its temperature rising imperceptibly slowly over the first 10⁻�67 years. Then, as it approaches its final moments, the pace accelerates. The remaining mass radiates away in an exponential burst that culminates in a final flash of high-energy photons as the last fractional solar mass of the black hole converts entirely to radiation. The flash is brief. The energy is modest, equivalent to a few million hydrogen bombs. In the vast darkness of the late universe, this flash is the most dramatic event in light years in any direction. And then, that region of space is darker than before. The supermassive black holes hold on longer, much longer. A black hole of 1 billion solar masses takes approximately 10 to the 90 years. Of 10 billion solar masses, similar to M87 star, about 10 to the 100 years. That number, 10 to the 100, is called a googol. It is larger than the number of atoms in the observable universe. It is larger than the number of atoms in 1 million observable universes. It is a number so large that our universe will have expanded by the time it passes to a scale whose relationship to its current size is itself almost impossible to express. For a duration 10 to the 90 times the current age of the universe, M87 star's black hole will persist. It will slowly cool. Its Hawking temperature will rise only as the square root of how much mass it has lost, imperceptibly slowly. It will be the last organized structure in its region of spacetime, the last concentration of mass and energy, the gravitational anchor of a region of space that has become, in every other way, utterly void. And then, at last, it enters its final seconds, cosmically speaking. The mass is small enough now that the Hawking temperature is substantial. The radiation is intense. The process accelerates in a final runaway. In a burst of energy lasting perhaps a fraction of a second, the remaining mass radiates away completely. And then, nothing. After 10 to the 100 years, the last black hole is gone. The universe contains photons and elementary particles expanding through space that continues to grow under the push of dark energy. The photons thin out. The particles move further and further apart. No two particles are ever close enough to interact again in any meaningful sense. The universe has reached maximum entropy, the heat death of the universe, the maximum entropy state, the end. Unless the information in those final radiation bursts is truly preserved, unless the Hawking radiation from the last evaporating supermassive black hole carries, in the extraordinary subtlety of its quantum correlations, a complete record of everything that ever fell in, every star that was swallowed, every black hole that merged, every gas cloud that was accreted, everything, encoded in photons, in quantum correlations between photons emitted over 10 to the 100 years, correlations so subtle that no physical instrument smaller than the universe itself could extract them, but real, preserved, written in the fabric of quantum mechanics. The entire history of the universe, written in light. A book that will never be read. Or perhaps the information in those final radiation bursts doesn't simply disperse into thermal radiation. It creates a new space-time, a new region of space and time, born from the death of the black hole, inheriting something from what was inside. And in this way, the universe ends by beginning again.
The question we have been approaching, the one that has been lurking at the edge of this entire conversation, is one that physicists ask only carefully and with considerable hedging, because it is the kind of question that sits at the absolute boundary of what physics can address. Is our universe itself the interior of a black hole? Lee Smolin, a physicist at the Perimeter Institute in Waterloo, Canada, has developed this idea into a full theoretical framework he calls cosmological natural selection. The core proposal is this: when a black hole forms in our universe, when a massive star collapses, when two black holes merge and form a larger one, it gives birth to a new universe. Not by creating a wormhole to somewhere else, not by being a portal in any sci-fi sense, but by the physical process of extreme compression and quantum bouncing that loop quantum gravity describes at the singularity. This new universe would have its own space-time, expanding from its own Big Bang, inaccessible to ours. It would inherit the physical constants of its parent universe, the strength of gravity, the masses of the fundamental particles, the cosmological constant, all the numbers that characterize our physics, but with small random variations like mutations in biological reproduction. The crucial insight is this: universes that produce many black holes have many offspring. Universes that produce few black holes have few offspring. Over many generations of this cosmic reproduction, the distribution of universes, in whatever multiverse this process creates, would be dominated by universes that are good at making black holes. Universes whose physical constants are near optimal for black hole production. Is our universe good at making black holes? Extraordinarily good. The particular values of the physical constants in our universe, the strength of the strong nuclear force, the masses of quarks, the value of the cosmological constant, all the numbers that characterize our physics, are collectively tuned in a way that allows stars to form, burn, and explode, seeding galaxies with black holes. Change any of these constants by a small factor, and the universe produces dramatically fewer black holes. This could be coincidence, or it could be that our universe is a descendant of a long evolutionary lineage, its constants shaped by billions of generations of cosmic natural selection toward the configuration that maximizes black hole production. The prediction is testable in principle, though not in practice with any instrument we currently possess. The physical constants of our universe should be near a local maximum for black hole production. Small changes in any direction should reduce the number of black holes produced. Several physicists have examined specific constants, the masses of quarks, the value of the strong coupling constant, and found that our universe is, indeed, close to locally optimal for black hole production. But this is not a definitive test. What is perhaps most remarkable about cosmological natural selection is what it implies about every black hole we have ever observed. Every stellar remnant black hole formed in the collapse of a massive star, every supermassive black hole grown through billions of years of accretion and mergers, every gravitational wave event detected by LIGO, every shadow imaged by the Event Horizon Telescope. Each of them, if Smolin is right, is also a birth, a moment of creation, a new universe expanding on the other side of what we see only as a dark and silent event horizon, evolving through its own cosmic history, perhaps forming its own stars and planets, and perhaps its own observers. We may be surrounded by universes, not in the way science fiction imagines parallel universes, not accessible, not reachable, not influenceable, causally and completely disconnected, but real, born from the same physics that gave us black holes, born from the violence and extremity and gravitational inevitability that we have been exploring throughout this journey.
And our own universe, with its particular physical constants, its particular history of star formation and galaxy evolution and black hole growth, may itself have been born this way, born inside a black hole in some parent universe we can never observe, carrying the inheritance of that parent's physics, modified by the small mutation that is the difference between our constants and theirs. The darkness at the center of every galaxy may not be an end, it may be a beginning. And we, formed from the elements forged in stellar explosions, living on a planet orbiting a star in a galaxy regulated by a supermassive black hole, capable of building instruments that listen to the space-time tremors of black hole mergers across 1 billion years, may be the universe's way of understanding its own origins.
We began in darkness. Not the comfortable darkness of a familiar room with the lights off, where you know what is around you even if you cannot see it. The absolute darkness of a place where light itself cannot exist as something that reaches the outside world. The darkness of a singularity in the equations, a breakdown in our best description of reality, a place where physics breaks down completely, irrevocably, and without apology. We began there because that is where the physics points. That is where the mathematics of a German physicist doing calculations in a World War I trench points. Where the orbital mechanics of a 20-year-old Indian student on a steamship to England points. Where the X-ray observations from a rocket launched in 1964 point. Everything pointed at the same conclusion, and for decades, physicists found ways to look away from it because the conclusion seemed too extreme, too strange, too much. Then we stopped looking away. We walked through the history of this recognition, from Michel's dark stars to Schwarzschild's exact solution, from the Chandrasekhar limit to the detection of Cygnus X1, from the stellar orbits of the S-star cluster to the Nobel Prizes that vindicated decades of careful, patient, often controversial work. We traced the arc of a scientific community slowly, reluctantly, and then with increasing excitement, coming to terms with the reality that these objects are not mathematical curiosities, but physical facts. We gathered the evidence. The orbital velocities of stars around SGR-A star, stars moving at thousands of kilometers per second, around 4 million solar masses compressed into a volume smaller than our solar system. The orange ring of the M87 star image, that perfect shadow, confirming the geometry predicted a century earlier. The chirp of gravitational waves carrying the echo of a billion-year-old collision. 2 black holes spiraling together, releasing more energy in a fraction of a second than the entire visible universe produces in that same time. And we felt it as a tremor in space-time, smaller than a proton. We went deeper. We found the M-sigma relation, the extraordinary proportionality between black hole mass and galactic bulge properties that tells us these objects grew together, regulated each other, evolved in concert across billions of years of cosmic time. We saw the cavities blown by black hole jets in the hot gas of galaxy clusters, the sound waves ringing at 57 octaves below middle C, the suppression of star formation across millions of light years maintained by a single black hole's jets. We ran the simulations without black hole feedback and found a universe that doesn't look like the one we live in. We added AGN feedback and watched the universe snap into alignment with observation. We accepted the conclusion. The universe we inhabit, with its particular distribution of galaxy sizes and star formation rates and chemical history, exists because black holes have been shaping it since the first galaxies formed. We confronted the deepest theory, Hawking radiation, the quantum mechanical temperature of black holes, the mechanism by which even the largest black hole will eventually, over timescales 10 to the 90th times the current age of the universe, evaporate into thermal radiation and cease to exist. and the information paradox that Hawking radiation creates, the collision between quantum unitarity and the apparent randomness of black hole evaporation, a collision that remains one of the most profound, unsolved problems in physics, and that hints at the existence of a theory of quantum gravity we have not yet found. We looked inward, past the event horizon, to the singularity where general relativity breaks down. We met the proposals for what quantum gravity might predict there, the loop quantum gravity bounce, the string theory exotic geometry, the firewall paradox that challenges even the most basic prediction about the experience of crossing an event horizon. We sat with the uncertainty, because sitting with uncertainty is what honest science requires when the questions are this deep and the answers are not yet in. We looked forward to the instruments that will deepen our understanding. LISA, which will hear the gravitational wave signatures of supermassive black hole mergers across the observable universe. The Next Generation Event Horizon Telescope, which will show us movies of accretion flows rather than single blurry frames. The pulsar timing arrays that have already detected the gravitational wave background, the cosmic hum of billions of supermassive black hole pairs slowly spiraling together throughout cosmic history. And we looked forward in time, far forward, to the black hole era, when black holes will be the last organized structures in the universe, slowly evaporating through Hawking radiation over timescales of 10 to the 67th to 10 to the 100th years, each one ending in a brief flash, the last one finally going dark and leaving a universe of cold, thinning photons expanding forever through a space that continues to grow under the push of dark energy. And then we asked the deepest question of all. What if those black holes, in the moment of their formation, give birth to new universes? What if our universe is itself the interior of a black hole in some parent cosmos? What if cosmological natural selection is real and the physical constants we inhabit were shaped by billions of generations of cosmic evolution toward whatever values maximize black hole production? We do not know. We cannot know with the instruments and the mathematics we currently possess, but we can ask. We can follow the physics to the edge of what it can say, and then stand at that edge and peer into the darkness. This is what science is. Not a march toward a destination already known, not the accumulation of confirmations of what we already believe. It is the willingness to follow the evidence wherever it leads, even when it leads somewhere uncomfortable, even when it requires revising beliefs we were certain of, even when the mathematics produces results that seem too strange to be real. Real in this universe turns out to be stranger than we imagined. The black hole at the center of the Milky Way is there right now. As you sit wherever you are sitting, the 4 million solar masses of Sagittarius A star are curving space-time at the center of our galaxy, bending the orbits of the S stars, occasionally accreting a small amount of gas and flaring briefly in the infrared. The last echoes of the Fermi bubbles expanding slowly outward into the galactic halo. It has been there for billions of years. It will be there, slowly evaporating, infinitely patient, for 10 to the 87th years more. We are only beginning to understand it. We are only beginning to understand what it and its siblings and cousins and the supermassive giants at the centers of all the other galaxies in the observable universe have done to the cosmos we inhabit. We are only beginning to work out, in the full mathematical detail that physics demands, what it means that information might be preserved in their evaporation, what it means that their interiors might be places where space-time itself breaks down, what it means that they might be the seeds of new universes. There is more to discover here than any single generation of scientists can accomplish, more questions than any current generation of instruments can answer, more implications, physical, philosophical, existential, than any single conversation can contain. Which is why this journey does not end. It only pauses. The universe is vast.
The mysteries are endless. The journey continues.